All right, class, welcome back. This is lecture 3. We're going to be talking more about sequences and more about limits of sequences and specifically more techniques for determining limits. And one new technique, well, not really new, it's called the squeeze theorem for sequences. So you've seen the squeeze theorem in Calc 1 to calculate limits of functions. This is going to be very similar. But first, some other things to use. Other rules you can use. So one is that it sounds fancy, but it's not so fancy. Limits pass through continuous functions. So this is just a fact we get to use. You would prove it in a much later class. And the idea is just that if you need to take the limit of something, and there's a function like eating everything, sort of like this one, then you'll be able to take the limit by passing it through the cosine. And the idea is just, again, it's because what we're doing is we're thinking about the limit of a function as x goes to infinity instead of the limit of the sequence, and we're just replacing the n's with x's, and then that way we get to use the rules from before. So in this case, the idea is, okay, I don't know how to do this limit, but I do know if I was just on the inside, I would know how to do that. And luckily, I can pass the limit through. So I can do the cosine of the limit instead. Often people just do this step all at once and they just jump right to saying what this limit is here. And so x goes to infinity, and x is on the bottom. So this is becoming a very small fraction. So it's really going towards 0. So then this is just cosine of 0, because that's what that limit is on the inside. And then cosine of 0 is 1. So then the idea is that now the limit of the sequence is the same as the limit of the function. So we can say that this guy converges to 1. Again, we're really just using Calc 1 stuff here when it comes down to it. Not really anything new. We're just sort of at the end saying something else than what we would have said before. So you could say that, or you could say this limit as n goes to infinity. And this means the same one. They both mean that the sequence converges to 1. Okay. So yeah, this is sort of at first seems like a weird sequence, because remember that this really means like plug in 1, plug in 2, plug in 3, and it's just a list of numbers. That's what this sequence really is here. And as you plug in those lists of numbers, as you go down and down and down and down, further down the list, what happens is that those numbers are going towards 1. And you can also sort of like verify it to yourself by actually using a calculator and plugging in numbers and seeing what happens. Or you can try to graph it on Desmos or something and see it as well. Okay, so another similar time that this works. So if you have something like the sequence and there's a big old square root around everything, and you know how to deal with this, I know how to deal with the inside, then we're in luck because we can apply the same type of rule because limits pass through continuous functions. And we're always dealing with continuous functions in this class, like cosine is continuous. The square root is continuous. So we don't have to worry too much, and we can just do this the same as before. So again, we consider the function instead of the sequence, and we consider the limit as x goes to infinity of the function Oops, sorry, that was a 2 on top. And then this, you can justify it with L'Hopital's rule because this goes to infinity over infinity because the top grows and so does the bottom. They grow very big as you plug in bigger x's. And that allows you to use L'Hopital's rule. But then there is also the shortcut. So L'Hopital's rule says take the derivative of the 2x plus 1, you get 2. Take the derivative of 3x plus 5, you get 3. But there's also the shortcut you learn in that section, which is like, because the powers of x, the biggest powers of x are the same on the top and the bottom, it's just going to end up being their coefficients. If it was like 2x to the 5th over 3x to the 5th, it would be the same thing. But you would have to do L'Hopital's rule like 5 times. So in any case, this limit, there's no x's in it, so it's just 2/3. All right, so this, I missed completely one thing, which is the point of the problem, this big square root. I didn't put that in. So how does that affect things? Well, the idea is that I should have been taking, do it in green here, I should have been taking the limit of this thing. But then what I'm doing is I'm passing the limit through. So it becomes the square root of the limit of these things. And then we just figured out that that was 2/3. So that's going to be a 2/3 inside of the square root. So that's what we should have actually had this whole time. Like that. Okay. So 2/3, square root of 2/3 is what the sequence converges to. Converges. Got to finish the problem by saying what it actually converges to, because that's what we're looking for. All right, so next up is the squeeze theorem. Again, another tool from Calc 1 applied to sequences. So next lecture is when we'll actually learn some new things. These are just the same things with different letters, is one way to think about them. Okay, so the squeeze theorem, but this time for sequences, works exactly like the squeeze theorem did before. So the idea is sort of in the name. If you have two sequences and you know what they do, you really need to know what they do first. Which both converge to L, some number L. So you know what these two guys already do. Okay, and if there's a third sequence between them, which I'll call Bn, I'll just say squeezed between the other two, then this also converges to L. Now, what does squeezed mean? It really means that your AN and your CN terms, so not the sequences, you're just looking at specific terms, they squeeze CN, I mean, BN means that BN is between them after some nth term in the sequence. So it doesn't have to always be squeezed between the other two. It just has to be squeezed beyond some point of no return, and then it's always squeezed between the other two, and then this will happen. Okay, so the other way to say it is, if you know this limit is L and this limit is L2, and you know that Bn is between them after some point, after some nth term, then you can also say that the middle limit, the limit of the middle sequence, is also L. In pictures, it just looks sort of like this. You already know that AN looks like this, maybe. It's going towards some value L. That's what it's converging towards. And you also know that this other one is going towards L, maybe from the opposite side or something. Then you automatically get to say, it doesn't matter what happens over here. So these are the B's. Maybe they're outside. But as long as you pass some nth value, after that point, they're between the other two always, then you know that Bn, the Bn's also have to go towards L. That's the visual for it. Okay, so let's do an example. The examples sort of always work the same. Find the limit of, or find what this converges to, however you want to say it. Okay. So the idea is that this thing, I don't really know how to do. So it turns out I actually do know how to do this one, but we're going to pretend we don't. And think about things that we do know how to do that surround it. So the trick is, whenever you see a sine or cosine, you're probably looking at a squeeze theorem problem. And that's because cosine and sine have bounds. They're surrounded by something naturally. And so that allows us to create this situation. And that's really the goal, is to create this situation. So you might remember cosine and sine are both bounded. They only go as high as 1 and as low as -1. So in this case, we're dealing with cosine, but sine does the same thing. And so you could replace it in a different problem and it would work the same. So you realize this first, and then you try to build that in the middle. By just multiplying or doing whatever you need to do to make it show up. And right now it's already almost there. We already got the top. We just need this. So to get that in the middle, I just have to divide all 3 terms by n squared. So I'll divide by n squared, and I get -1 over n squared less than or equal to cosine of n over n squared less than or equal to 1 over n squared. And you do have to justify whenever you're dealing with less thans. You have to say, like, why do these stay the same direction? Because if you remember something like this, if you multiply by a -1, it does flip it over. So you have to say, like, why do I know that these don't change direction? And it's because n squared is always positive because you're squaring something. And when you multiply by a positive or divide by a positive, it doesn't flip it. So that's why these don't switch directions. Okay, so then once you have this set up, you should also say, like, when is this true for? Well, this is true right away for n starting at 1. But in other problems, it might not be true until later, but it has to be true at some point, and then from that point forward for this to work. Okay, so now that we have this, we just need to say, like, do I know these limits? And I do, because those are just like what we did on in the previous lecture. If you only have powers of n, or when you're talking about functions, powers of x on just the bottom, and there's just a number on top, and you go to infinity, then the bottom will grow infinitely big, creating smaller and smaller fractions, making this list, the terms in the list shrink and shrink and shrink. And so they're heading towards 0. And it doesn't matter if you're coming from the negatives or from the positives. It'll still do the same thing. They'll both go to 0. And so you say, well, something like by the squeeze theorem. I don't remember the spell squeeze. So by the squeeze theorem, you can conclude that the limit of the inside is the same as those two. So if those two were not the same, then this wouldn't work, because they have to go to the same place to squish the middle into the same thing. The idea being, what's the only number between 0 and 0? Well, it's got to be 0. There's nothing else that this could possibly be. Whereas if this went to 5 and this went to 3, then there's a whole bunch of numbers between 5 and 3. So you can't really say what it would go to at that point. They got to both go to the same thing for this to work. Okay. So let's do another example that's a bit trickier. Let's determine what this converges to. So if you just sort of think about it, you can already imagine that it's going to go to 0, but it's hard to show it with stuff besides the squeeze theorem. So if I just sort of start plugging in numbers, so I plug in 1, I get a -1/2. I plug in 2, I get +1/4. Then I get -1/8 when I plug in 3, and then it just keeps switching back and forth, and the bottom keeps growing. So it seems to go to 0 because it's just jumping back and forth. But while it's doing that, it's shrinking towards 0. But that's not a great proof of why it converges to 0. And the squeeze theorem allows us to actually show it for real. Okay, so let's see. So we need this limit. And there's nothing I can do. I can't just say, okay, n gets really big, this goes to 0. It's not the same as this sort of situation where I could do that. From yesterday, we said that this will go to 0 as long as the number in here is a fraction less than 1, which it is. So I could do it if it was just that, but it's not. It's got this pesky negative in there. Okay. But this gives us a hint at what we could do. So I do know what that does. And I also know what this does. If I just get that negative on the outside somehow, then it's going to work exactly the same. It's going to be -0, which is still just 0, because this guy is less than 1. So as n gets very big, that limit becomes 0. And now I just have an extra negative on the outside, which doesn't matter because it's just -0. And these two are actually related to this one. So it's going to work out nice. Let's see if we can think about it. So let's write out these sequences. So we have 1/2 to the n is just 1/2 1/4, 1/8, 1/16, and so on. If I stick the negative on the outside, then it just makes all of these be negative. And if I stick the negative on the inside, then it flips it back and forth. Starts off as negative, then it's positive, negative, positive, so on like that. So we can actually relate these in a nice order. So what's bigger, 1/2 or negative 1/2? Well, the positive one is bigger, right? So in fact, this is our bn that we're trying to make be in the middle. This is going to be our smaller one, an, and this is going to be our bigger one, cn. So we can see that negative 1/2 is less than or equal to, because it's equal to negative 1/2, and that's less than 1/2. So we have an, same color, is less than bn is less than cn. Less than or equal to, for those ones. And then the next one, I think it's still true. It's always true. Let's see. So 1/4, is that bigger or equal to 1/4? Yes, it is. And is that bigger than or equal to negative 1/4? Yes, it is. And what about the next one? Is 1/8 bigger than or equal to negative 1/8? Yeah. And is that bigger than or equal to negative 1/8? Yeah, because they're the same. So in general, you can definitely say that the negative being in the inside creates a sequence whose terms are squished between the terms where you take the negative on the outside and you don't have a negative. That's what's going on here. And so this is letting us use the squeeze theorem. And that's because we know the limits of the outsides now. So then, since this limit we already had said is 0, and it's the same as the one on the right, then the limit in the middle is the same as well. So we never actually calculate this limit by doing anything to that sequence. We only know what happens to the outsides, and it tells us what happens to the inside. Okay, so that's a slightly trickier one where there's no sine or cosine. Okay. So one thing to notice is it doesn't really matter that it was a half. So the same trick would work for if it was like negative 2/3. You could do the same exact trick. So in fact, it would work for any negative number to the n, where as long as it's still a fraction, then you could do the same tricks. So this has to be less than or equal to 1 and 0, be between 1 and 0. So then the same exact trick will work. And so really what this means is, before we said this converges when you're between 1 and 0. So specifically, it converges to 0 unless r is 1, because then it's just a bunch of 1s. But if it's below 1, like 1/2 or 2/3 or something like that, then it'll just shrink and shrink to 0. But now I can also extend it to negatives. I can say it converges when you're between -1 and 1. So if it's exactly -1, actually, sorry, exactly a -1 is not going to work, but everything else will work. So we have to take that off. And that means we have to take this off as well earlier. Sorry. So it actually doesn't work at -1 because if you do this, there's no, the limit does not exist. And that's because the sequence will just look like -1, 1, -1, 1, -1, 1, flipping back and forth forever, and it's not shrinking, so it's not going towards 0. Whereas if you're a little bit above -1, like -2/3, -3/4, -1/2, things like that, then the argument that we just did will show that that limit is also 0. Okay, so this will be 0 as long as you're strictly between -1 and 1. It won't exist if you're exactly at -1. And it'll equal 1 because it'll just be a bunch of 1s if r is 1. So those are the 3 situations that can happen. Okay, so I want to do one more example of the squeeze theorem. Let's see it. So instead of writing this sequence, I'll just jump to this. Let's find this limit. And see what we can do here. So this time we have a sign. It gives us the clue that that we could use the squeeze theorem successfully. So sine is stuck between 1 and -1, so that gives us a starting point. And then we just want to build this in the middle using algebra. So we can't just do weird things. We got to make it make sense. So the first thing we can do is let's try to divide by n. So why is this okay? Well, it's because when you're taking the limit as n goes to infinity, you're not worrying about negative numbers for n. N starts at 1, so 1, 2, 3, 4, 5, and so on. So you're never dividing by a negative. So these guys, we don't have to worry about them flipping around. So next, I do want a negative on my sign. So now I'm going to multiply by -1. And that will flip everything over. So this will become +1/n. The directions of the greater thans will flip. And we'll get that. And then I want this 2n in there. How can I do that? Now I'm going to add, well, I can't just stick a 2n in there. That doesn't make sense. I have to have a common denominator to add fractions to get something in there. So I really have to add 2n over n to all 3 things, which is really just a 2. And so if I add a 2 to all 3 sides, it doesn't change the direction of the arrows again. And then this will give me what I want in the middle. Okay, so here we got 2n plus 1 over n is greater than or equal to 2n minus sine of n over n. Now we have exactly what we want in the middle. 2n plus 1 over n. Oh, wait, one of these should be negative. What happened here? Aha, I forgot to make this one be negative when I multiply by -1. So this will be negative now. And so this will be a -1. Okay, so now we have what we want surrounded by two things. We got to take the limit of those two things and hope they go to the same place, which I believe they do. So in this kind of problem, we're using some shortcuts here. So for example, this limit, what you really do is you use calculus, you change it to x's, and then you can use L'Hopital's rule or the trick that they have the same power of x. So this will just become a 2 over 1, which is 2. But often once you get used to this stuff, you sort of skip all this part. And you just assume that everyone knows what's going on. So you just implicitly do that. Okay, so that limit is 2 on the left. This will be 2 as well for the exact same reason. So the two outer ones go to 2. That means the middle one also does as well. So this guy. Also by the squeeze theorem. Okay, so that is it for today. I will see you next time.